Okay, so let me go over this. Okay, statements and what we can do with them. Some of these transformations change the statement substantially, and other only change the form. Okay, so so once again, the contrapositive is the same statement. Negative is certainly a different statement, and the converse is also a different statement. Okay, so then producing the contrapositive is just helps you to understand the problem. There may be a different approach for proof that you're looking for. The negative is, it is the opposite of the statement itself, so that's crucially different. So to make that point clear, one thing to use is truth tables. Okay, that these are on the right. So here these two were used in particular for combining two different statements. Whether with or and as you can see, they are combined in a different fashion. But the truth table is actually relates the tells us pretty much everything that we need to know about the relation between the three statements over here. But you could have two statements, and let me make that clear. What I just talked about as far as the contrapositive is concerned. So say statement A here, it could be true or it could be false. Okay, contrapositive of A, what should I put here? Statement A is true. Can you say anything about the truth? The true, whether the contrapositive is true or not.
If statement A is true, then the contrapositive is true?
Yes. Well, and what about false?
It's false.
It's also false. Okay, so in other words, they either both true or both false. Okay, so if one is true, then the other is true. Okay, so that is another word for it is equivalent. So not only contrapositive statement and its contrapositive are equivalent to each other, but there are many statements there are many ways to transform a statement into an equivalent statement. So, well, x is equal to 3, x is equal to 4 minus 1. Okay, here's our equivalent statements. Okay, so ideally when you're solving equations, for example, you transform every equation is a statement about x. Ideally, you transform it into a new statement which is simultaneous, is just as true as the original. So either for each x, it's either the two statements either both true or both false, right? Look at these. And ideally, you go in both ways. Frequently, you'd go only one way, and that might be questionable. So another equivalent statements would be, say, x squared is equal to 1. Well, this is the symbol of equivalency, by the way. So it goes both ways. So A, so let's call it B. So we have A implies B, but also B implies A. Okay. And if you go both ways, then you combine these two symbols into one, and then you have A equivalent to B. Okay, so that's the notation that we're gonna use. It is used a lot in mathematics, even though 99% of the time you can get away without any kind of symbolism like this and just with words. But it is a tool. It is a tool, and it makes things really compact, and it might help you to make sure that your thinking is valid. So let me, what symbol should I put here in between these two statements? One statement is x squared is equal to 1. The other one, x is equal to 1. Is there any relation between them? statements cannot be equal. Numbers are equal, sets are equal, and actually the equal only, well, that's a fair point actually, since we talked about that last time. It is the relation between, on one hand, statements, on the other hand, sets. Remember that discussion from last week, yeah, no, it was yesterday. Okay, so equivalence is the same equivalence of statements. Over here I have, so these are statements. But if these statements correspond to sets, they are indeed equal. Okay, so in other words, what we're talking about here is the solution sets. Okay, solution sets. There's an equation. There is a solution set. All x that satisfy the equation, or inequality for that matter, or a system of equations. Okay, so that solution set is something that allows you to translate the language of statements, statement A, statement B over here. It allows you to transform that into the language of sets. So then the language A, then the set A is the solutions, all the solutions of x squared is equal to 1, and B is all the solutions of x equal 1. Okay? So then you have simultaneously two questions asked. What is the relation between the two statements over here, A and B on one hand? And the answer will be pretty much the same about the relation between these two sets. So, well, let's start with the statements one. So back to the statements. Statement x squared is equal to 1 about some x, or all x's, about some x. Okay, and then B is a statement about x again. So what's the relation between them? Well, you have solved the equations, right? So x squared is equal to 1. What do you do with it? Okay, so what do you get?
X equals 1.
All right, so I did. Okay, so once again, you proceed from one statement to the next. You have to make sure, or you have to be clear about the relation between those two statements. So what's the relation? What?
They're equivalent?
Are they? No.
They're both equal to 1.
No. No.
Can x be plus or minus 1?
Plus, see? So they're not equal, right? So you can discover that if you, once again, if you go to the bottom and interpret this in terms of sets, then this set consists of one element, 1, and this set consists, the set A consists of what?
-1.
-1 and 1. Okay, so they are not equal. Okay, so then these two statements then are not equivalent. But it doesn't mean that we have nothing to say about them.
Well, can't B be towards A?
Right, so A implies B. I'm sorry,
Yeah.
the other way, thank you. Yeah, the other way, like this. So if x is equal to 1, then x squared is equal to 1, right? But not vice versa. So just to make that clear, let me do this. Well, let me change the color here. Okay, how about this? So it goes this way, but not the other way. Okay? So once again, if x is equal to 1, then x squared is equal to 1. Okay, but just because x squared is equal to 1 does not mean that x is necessarily equal to 1. Okay? So that's the two things that can happen between statements that are related. That might be unrelated. It's quite possible they may be talking about different things whatsoever. Okay, different equations. And now, since we have started with the sets theory already, so once again we just explained why we cannot say so these are not equivalent, but still related, and one implies the other. Okay, so now, and we explained it why that's how we discovered that they're not equivalent, because those solution sets are not equal. Okay, but once again, they are related. So they are not equal, but what? What's the relation between those two sets? One and negative 1, 1. What?
That B applies to A, but A doesn't apply to B.
No, I'm talking about now about they're not. It won't be implication. It's sets now, not statements anymore. So what is it? What if you remember the term? What? Subset. So this term is the implication. One statement implies the other, and it corresponds to a set for sets. The corresponding idea. I made it this big symbol, but I hope you understand this is what I'm talking about. It is just like that union symbol, like a U on its side. Okay, so once again, one of them is bigger than the other. One contains the other. In other words, that smaller one is a subset of the bigger one. Okay, so you can whenever you are able to transform those statements into sets, then the relation between the statements will correspond to certain relations between the sets. Just like over here, remember we did a very similar, not very similar, but we followed the same idea. And once again, we had transformations of relations between well, these are actually combinations of statements were mirrored by combinations of sets. Okay, so at the top we have two statements combined with words and or, and with those symbols you might remember once again these are the two symbols how to combine the statements, and they were now corresponding sets were combined at the bottom with symbols of or operations of union and or rather intersection and union. Okay, so if we require then look at these. First statement at the top, we combine them with the word and. So this is and this is or. Okay, so as you can see, the symbols match. The symbols match whenever you combine the statements with and statement. The symbol is the upside down, and it corresponds to the symbol of the union. So this is the match. Okay, so once again, this is and this is or. And one it corresponds to the union, to the intersection. The other one corresponds to the union. Okay, so once again, all the operations that we'll have with the statements, they will match by statements by the operations with sets. Okay, so once again, and gives you intersection or gives you the union, and over here we have implications gives me a subset. Okay, all right. So there is one more operation. There's one more operation, but let me finish this example. There is a point here, so one more example. So statement A is still x squared is equal to 1. And I want to have a statement B that starts with x equal 1. I'm not sure how to write this. Let's just put it this way. Okay, so one statement is the same as before, x squared is equal to 1. The second statement is statement B, which starts with x equal 1. How do we finish this? The second statement.
It has to be equal to 1 and negative 1, right?
Right, so we know that for the two statements to be equivalent, we have to also take care of the possibility of negative 1. So what do I write there?
An absolute value?
No, I don't want to do absolute value. I want to have x equal 1, and I want to have x equal negative 1.
Okay.
The question that I'm asking is, what is the question I'm asking? Or the missing part, right? The missing part in between these two statements, x equal 1, x equal negative 1, and the missing statement is either and or. Which one is it? Or, yes. Or. Okay, so when x is equal to x squared is equal to 1, then either x is equal to 1 or x equal negative 1. And vice versa. If you have a number x where you have you say something about x is that it's either 1 or negative 1, doesn't matter, the result will be still x squared will be still be equal to 1. Okay, so unlike the previous example when we had implication one way, x squared is equal to 1 is implied by x equal 1, but not vice versa. This goes both ways. Okay, so and then you can certainly see then. So these are the statements. What about sets? This is negative 1 1 is equal to what? What? Negative 1 union 1. Okay, so as you can see, the correspondence is complete. Even I can instead of or I could put this little symbol here just to remind you that it is about unions. Okay, so so these are the major operations that we have on statements. So far, unions. I'm sorry, and or and union intersection. We have subsets. And what's left is negation. So negation, it's another operation on statements. So as far as the equations such as these are concerned, it's very easy because, well, what is the negation of x equals 3? What?
X equals negative 3?
No.
Negative x equals negative 3, right?
Negation or the negative of. Negative of. Remember, yesterday we talked about the universe. It's like a statement. There's the universe of statements, and you pick one of them. The negation is the rest of the statements. X equal 3. Negative of is. It's simpler than you think. So not equal to 3, that's all. Or x larger than 5, negative is what? Less than or equal to. Okay, so whenever it's about numbers, it's frequently very straightforward. Okay, so once again, these are about statements, but on the other hand, so these are statements. So the negative or the negation or negative of, negation sounds like an operation, and we're talking about the negative, which is a statement taken together. Look at the two statements together. They take care of all possibilities about x or anything. It is called the law of excluded third or excluded middle. So it's either x equal to 3 or it is not equal to 3. There is no other possibilities. It's either x is larger than 5 or it is less than or equal to 5. There is nothing else left. So there should be no, when you do this, there should be no gaps left. And in fact, it is, if you now switch to sets, what it's going to look like, it's x equals 3. This is A, let's say. And then, well, A, 3. And then B is the rest. So you exclude 3, and you take one point out of the set of real numbers, and then that's what you're left with. 2 raised x not equal to 3. Or this one from 5 to infinity, that's A, excluding 5. Okay, so that's my A. And then its complement, so this is A and this is B. A, B. And it will look like this. This is B. Everything from negative infinity to 5, including 5. Okay, the notation for the, well, what's the term, if you know, for what's happening on the right? The two sets, A and B, what's the relation between them?
Not equal.
No, they are not equal, no, but that's not there is a very specific relation between them. The word is complement. So A is the complement of B, B is the complement of A. So they complement each other to create the whole thing. Okay, so that's with sets, and the same with the statements. Okay, so the notation is for the negative, it's either a bar or a with that symbol preceding it. So that's how you negate it. And then for sets, it's either, once again, bar. When the whole set is indicated, then you just put a bar. When it's not indicated, then you just have to put a bar. But when the ambient set is indicated, then you can put it this way. That might or even x minus a. Another possibility. Right, so the total ambient universal set of all possible points or objects or numbers in the discussion, and then you say, in this case, x is equal to r, the reals. Okay, so you exclude it, and as you can see, sometimes it's used, the symbol uses simple subtraction, which is kind of literally what's exactly happens. You take all the real numbers and throw out some of them, and what's left is the complement. Okay, so that's what we see on the right. That's what has happened on the right. And then it totally matches what's happening with the statements. We are primarily interested with what's happening with the statements right now, but certainly all of these, this terminology and the notation is used extensively, even though it's half of the time you can get away with nothing but just plain language. Okay, so to summarize. Let me try to summarize what we have now. Okay, so either sets or statements. So we have what would be the equivalence. Well, probably let's start with implication. A implies B. Okay, that's number one that we have learned. Number two is equivalence of statements that are implied. A implies B, B implies A. That's the second one. Okay, number three is the and. There is no nice word for it, so I just say and. A and B. Okay, so well, I guess A, B. Okay, number four is A or B. The notation is A, V upside down B. And now finally the complement, or the negation, A bar, the negation. A bar. Okay, and I'm not going to write this, but they have all the, we have a corresponding notation as well as terminology for the sets as we have for the statements. Okay, so that's pretty much the basic of the logic that you're gonna be using. In a very careful manner, because that's what mathematics to a large degree is. It is doing logic in such a way that whatever comes out would be rock solid. Okay, so in addition to knowing the subject matter real well, such as calculus, for example, then to actually prove things mathematically requires very, very careful logic. So not skipping steps, not making logical mistakes, which is unfortunately multiple, and for example, confusing contrapositive with the converse, or just taking the initial statements and thinking that it is converse. Correlation is taken for causation and all of that. So all of that we have to try to avoid as much as possible. Well, we have to actually totally avoid them. Since it's mathematics, unfortunately, well, why it is actually a plan that can work because we're doing mathematics, not, I don't know, politics, because we are choosing to study things that are actually can be handled with care, and it works out. Okay, so everything is defined very carefully, and that's why the logic is applicable, and we can actually succeed in using logic in comparison to outside world where everything is fluid and uncertain, and we're not, probably logic doesn't work as well, unfortunately. But at least here it succeeds, more or less. So it's worthwhile. Okay, so let's see. Okay, so let's just have a few more examples of non-numerical illustrations or examples of these ideas. So give me a few examples. So implication. Give me an implication that is not about numbers. What?
So an implication that's not about numbers?
Right. That's right. Yes, I wish it's correct example. I just want you to give an example that hasn't been done, but it is exactly it. Yes, certainly, or vice versa, anything. So the statement does not have to be correct, by the way. So that's fine. We'll be treating incorrect statements just as carefully as correct statements. In fact, that's the way to find out whether a statement is or is not incorrect, is to treat it fairly until it breaks down. We reach a contradiction. So that's how we prove things often. Once again, we start with the premise that we know or think we do is incorrect, and we treat them in a logical manner until we arrive to a statement that is known to be false. Then we'll know that the original statement was untrue, and that's how roughly it works out. How long that sequence of statements is unknown ahead of time, but if Z is false, then A is false. That's you can have a truth table for that one too. So there's a truth table for every one of them. But let's do examples first. So any other example of implication? Something that we haven't talked about yet. You can do it from mathematics. Think about, we had one example from mathematics, as long as it's not about numbers again. So for example, function, we did yesterday. If function is differential, then it is continuous. That's an implication. Can you think of anything like that from calculus? If it's continuous, then what? Well, okay, fine. Like I said, it doesn't have to be correct. So that statement is false, so I have to mention that just in case. But it is an example of an implication. So if function is continuous, then it is differentiable is an implication. Okay. Now equivalence. So once again, you can think of example outside of mathematics or from calculus.
If you ride your bike, you're getting exercise.
Well, that's an implication.
Oh.
Because
Well, vice versa doesn't work, right? So it's not equivalent because you could get exercise without riding a bike.
Yeah.
Okay, so we are moving to number 2. So any example of equivalent statements? Well, once again, it doesn't go back. So I guess you don't see a lot of that outside of mathematics, equivalent statements. But in calculus, certainly, in calculus, okay, let's do numbers again. So, well, if we are allowed to have incorrect statements, you can just say anything you want, and that's fine too. As long as you understand what you're saying, it's easy to make sure that you understand what you're saying if the statement is correct. But if it is not, maybe not. Yeah.
In football, if you score a field goal, you get 3 points.
Okay, because you cannot score 3 points in any other way.
Right.
Okay, so that works for me. Okay, so 3 points equivalent to field goal. Yeah, so you can think about law and order situations when there's a specific punishment for a specific crime, and there is no other crime has the same punishment, for example, or credit for that matter. So, for example, another one, if you're getting D or higher, you pass the class, and there's no other way to pass the class but getting some D or higher, right? So that's another equivalent statement. Okay, let's think about and statements. So anything outside of mathematics, that creating a new statement which has some meaningful let's see. Anything? So ideally, two statements that are not complement. What happens if they're complementary? By the way, so two statements that are complementary, and you take the union of them, what happens?
Everything.
You get everything, right? So it's a x equal to 1, x not equal to 1 together. You have all the possibility. So you can probably think of situations when that happens outside of mathematics, or at least not with numbers. Well, if you want to calculus, then functions are differentiable, not differentiable. They're complementary, so it's one or the other. But anything, just right now, I don't have anything more interesting. So let me just take a moment here and put the so like this. So be careful with the sets versus statements. As you can see, the inclusion symbol that in black one points in the direction opposite. So you're when you're going from A to B under implication, you narrow things down. Possibly if they are equivalent. If they are equivalent, it's the same statement. If not, then you narrow down your possibilities. So once again, function continuous and differentiable. You say then it is differentiable, but there are fewer. I'm sorry. The correct statement would be if f is differentiable, then it is continuous, and then you're widening the set of possibilities. Yeah.
So for the implication, if A implies B, then you put the symbol that way, like you have it.
That's
or
like this. Yeah.
Okay.
Sorry about that. So as you can see, I guess the narrow part is on the same side.
Yeah.
It seems like you want to go in the you go from A to B, and then you want to go A includes B, but it's the exact opposite.
Right.
You can see why, right?
Yeah.
So once again, x is equal to x equal to plus or minus 1. No, x equal to 1 implies that x squared is equal to 1. Okay, so you widened. No, you narrowed down. Hold on a second. No, I think I messed it up. That example messed it up. Okay, so when it implies it, no, we are going wide. So sorry about that. I went exactly. So we are widening. We are widening the realm of possibilities. So once again, the function is differentiable, then it is continuous. There are more continuous functions than differentiable functions. If numbers, let me give another example to put this to rest. X larger than 3, then x is larger than 1. Okay? Right? So the set of x numbers larger than 3 is included in the set of numbers larger than 1. So, and you have more and more. Okay, so that's the direction of the implication, that this one is equal. Okay, so the two sets, and they're just equal to each other. Just all of these examples of numbers are very convenient. Say x squared is equal to 1 if and only if. That's another way to put it. X equal plus or minus 1. That's the same. So just restating equivalency is, logically speaking, it might look very different, but we're saying the exact same thing because they are simultaneously either true or simultaneously false. So that's why that's what we do in here. A union B. I can think of an example right now without any kind of okay, so A is math major and B is physics major. Okay, so math major, physics major. And then if you want to combine with the information above, then I could, let me use the right symbol here. So we're talking about a person being a math major, and then we could say, or is a physics major. And I put here, what if I put science major here? What's the symbol there between them? Right? So whether you're a math major or you're a physics major, you are a science major. Right? And once again, you can think about sets. You take the set of math majors, you take the set of physics major, take the union, and that union is a subset of the set of all science majors. Okay? So, but there is a subset, it does not go backwards. So there are science majors that are neither math major nor physics majors.
You're saying or, but I thought that's an and statement. Or is
Oh,
it-
I'm sorry. I messed
Oh,
up the
maybe.
letters at the very beginning. This one, yeah. So I was talking about or and. Okay, let's do the and okay, and A, B. Okay, so I want to take majors again. So math major. Once again, it is possible to have and physics major. Implies, how about double major? So if you are simultaneously math major and physics major, you are double major. Okay? But not vice versa, because they are double majors that are not these. Okay. And negation is, well, anything really. So not a math major, not function not differentiable, not equal to something. So all of these will encounter. Okay, so so we have to take it to the next level now. And the statements are what we started with the couple of days before. It is the if-then statement. So this is implication. I guess I didn't make that quite clear. Unlike the sets, look at the A is a subset of B. That's pretty much the end of it. But if you look at the on the first column, that what is A implies B, there is A statement, B a statement, and then A implies B is what? It's also a statement. Okay? So A implies B, A is a statement, B is a statement. You say, then what you're saying, you're stating that A implies B. That's a new statement.
If A
That's right. So it is. We are back to if-then statements. So if A, then B. And A and B could be, once again, compounded statements. So this is a way, just like algebra, this is algebra, we can form more and more complex statements if we are just put anything, we can put anything there, as we just did. The example that we had was very simple, F differentiable, F continuous, so these are simple, but you realize that, and we have seen already examples of when A could be, at its simplest, it could be, for example, an or statement, or it could be equivalent statement, or negation statement. So as an example, let's say, how about F is continuous
If you flip it, would that statement be true then?
what?
If you flip it, would that statement be true then? If F is differentiable, then F is continuous?
No. So this one is false to begin with, so this one is true. Differentiable implies continuous. I wanna just what I'm talking about right now is the how we have these simple rules or operations can be combined in to produce statements of any complexity, and just as I said, so whatever complex statement A you have and statement B you have, you combine them into the new implication statement, and then you have a new, more complex statement. So let's do some. Well, actually, let's well, it's pretty hard to, the examples that we have are hard to combine. So the first example about functions continuous differentiable, the second one was about football. So it might be hard to combine them, but maybe let's do it. Let's have an example of with numbers. I think that would be the simplest one. So x larger than 0, x less than 3, and. Okay, so as you can see, and b could be x equal to 3 or x equal to 5. Okay, here we go. So that is a compounded statement. So there are 4 statements originally: x larger than 0, x less than 3, x equal to 3, x equal to 5. These 4 statements are combined into one statement with the implication, as well as and or statement. So if I take this and I want to use just the symbols without letters, I'm going to have x larger than 0. Just like in algebra, good idea to separate the statements with parentheses. And x less than 3 implies x equals 3 or x equals 5. Okay, so that is a typical way how we can create any statement that you want. On the other hand, it is more typically you have a complex statement and you decompose it into elementary statements with very specifically indicated connections. Question?
I'm confused.
Yeah. Okay.
I don't get that.
Yeah, wouldn't 5 not, doesn't that create a domain? Like, isn't that?
Because you said that x is greater than 0 and it's less than 30.
I'm not saying the statement is correct.
Okay.
Oh.
Oh, okay.
I made it up.
So it's negation? What are we doing?
No, entirely. I had statements came from somewhere, and I just put them together into
Also,
one
this is
statement.
random.
Yeah, it is exactly random. Yes, it does mean, however, that you are not going to examine it and just say whether it's correct or not. So, is it true or false? So x is larger than 0 and less than or equal to less than 3. Does it mean that x is equal to 3 or 5?
Okay.
Yeah. True.
You're just putting an example up there, just how to write it down when you're given all that stuff?
Yeah, you like I said, incorrect statements have to be treated in the same manner.
Yeah.
So I combine it, and it looks complex, and nobody so far has been brave enough to say that it is false. It is false. Okay, false. And how do you prove that it's false? No, you have to be more specific. Well, I mean, let's look at with the statements. It might be more complex. Let's use this opportunity and translate it into sets. 0, infinity, intersection, negative infinity, 3. What's the symbol? Inclusion. X equals 3, union, x equals 5. Okay, so that is the same. So the question is why, and we answer the question by translating this complex statement into statement about sets. The statement is about numbers, so we can treat it as if it is about sets of numbers, and that's what I did, right? So x larger than 0, it's all x is larger than 0, 0 infinity. Then the second, negative infinity 3 is my second set, and then implication means inclusion.
Well, just 3 and 5 don't fall within the range or whatever on the left side. I mean, you're only going from 0 to 3, not including them, and then on the right, you're trying to say that 3 and 5 fall in there, and they don't.
So wouldn't it be like
Right.
a negation? Because they go.
No, it's not you see, the negation and the statement is not false. The statement is false does not mean that the negation is true.
It's just false.
It's simply untrue. Well, no, negation is true. The point is that it is, no, the negation is false if this is true and vice versa. But to prove that it is false really has nothing to do with the negation. All you have to do is that to demonstrate that there is one value on left which is not on right. Give me one number.
That's on the left.
Yes, but not on the right.
1.
1. Okay, so 1 is on the left, not on the right, which means that there cannot be inclusion of... so 1 on the left, no 1 on the right, so it's not included then. Okay, that's all. All right, so I guess we'll just stop here.